Some of you may know this joke. I think the corollary is very nice. This is what we're going to do. This is a piece of text, and now we're going to evaluate the amount of scientific reasoning. And we're not coming back to hell or heaven, but we're going to evaluate later a couple of these cases where you get a piece of text and basically you're asked to evaluate this in a more or less structured way. And here, the proposal is to evaluate these kind of things using a so-called 6-step program. It's also known as the didactico method. I think that was the term. So there are 6 steps involved, and the first step is define your real world. And that is the focus of the study, so what are you talking about? And you should realize that this is not rocket science. So I cannot tell you if we read a certain text, then your real world may be different than yours, than mine. That doesn't matter. But if you choose one real world, then your 6-step program must be coherent. So quite often we arrive at the same real world. We'll see examples later on. The second step is a model, and a model is to be interpreted broadly. I know that econometricians, my own training, with models you only think about a set of equations, but it can be a flow chart, it can be a graph, whatever, next year's model, or it can be a theory or whatever, just words. From the central question, that's why we're doing this, is does the model fit the real world? And the way to check this is derive a prediction or hypothesis from the model. So, for example, it could be the case that the model is a big theory and that the prediction is a rather specific hypothesis. Then you get data from the real world, and of course you're going to test your prediction against the data. So that's the question: do the data agree with the prediction? And that yields steps 5 and or 6. So in step 5, the question is, do the data agree with the prediction? If the answer is no, the data do not agree with the prediction, then your conclusion is, okay, the model does not fit the real world, so you can throw your theory out of the window. However, if the data do agree with the prediction, then we have to perform another step, because then we cannot arrive immediately at a conclusion. So, in that case, the next question is the match between data and prediction, is it likely that it would have occurred even if the model does not fit the real world? And if the answer to this question is no, then the data do provide a sufficient amount of evidence that a model fits the real world. If the answer is yes here, for example, because you have an alternative model that yields the same prediction, then the data cannot say something about a fit between model and real world. Oh, we're going to use this anyhow later, so. knows where student number 20 is? Mr. Hiddink. He wasn't here last week. Nothing serious with him.
I can ask if I see him on Facebook.
Well, I mean, he doesn't have to be here. Neither last week, but just.
He still exists.
He still exists. Okay. Alive?
Yeah, he's still alive.
Okay, good. He's not a member of Vindicott?
No.
Okay. Sorry. Anyone? So let's check. Here is an example, and this was a former PhD student in economics. And she was interested in, that was her real world, in a paper that she presented, and radio broadcasting in the Netherlands, and the feeling that, in general, listeners dislike commercials. So she built a model for that, an econometric model. It was a nested logic model, where the number of listeners depended on the number of commercials. And her prediction was that if the number of commercials goes up, then the number of listeners goes down. In other words, she predicted a negative coefficient in her regression. And she had some data on the number of listeners and the number of commercials for 5 Dutch radio stations over a certain period of time. And, well, the question, do data and prediction match? She found a positive coefficient. So that means end of her PhD career, throw away the model, her model, and throw away her out of the window. But that is usually not what happens. I mean, we do not throw models, theories quickly out of the window. It would be an awful amount of garbage outside in that case. Very often here you have, who would like to stick to your model? So very often then you take a next step. Because here there's a mismatch. Now, where does it come from? Well, one possibility is adapt your real world. Perhaps you made a model for something else. Or adapt the model. In both cases, for example, adapt the real world, a lot of her data were for commercial stations. So adapting the real world could possibly be something like the real world is it applies only to public radio stations, not so much to commercial radio stations, because there people apparently know that they're half of the time they hear commercials. Or adapt the model where the number of commercials depends on the number of listeners. I mean, if you have a large group of listeners, that attracts money from firms who want their commercials to be broadcasted, etc., etc. So in that case, there is also a causal relation the other way around. And in that case, you should build, for example, do something about endogeneity or build a simultaneous model, for example. And this is what we as a scientific community, what we very often practice. The outcome tells us throw away the model, but that is not what we do, because very, very often we love our theories, we love our models, and we want more before we throw it out of the window. So then we start fooling around. That's what we typically do. Here is another example. How are babies made? That is the real world. Here is my model. I'm sorry for the foreign people. This is a Dutch model. They are brought by storks. For the foreigners, little children, we do not want to explain them at a too early age, about the bees and the whatever. So we tell little children that babies are brought by storks. There are some other countries where they find babies in the cauliflowers. So this is the Dutch model. This is how babies are made. So the prediction is here, if the number of storks go up, then the number of newborn babies should go up. And someone gathered monthly data for storks, the number of storks flying over, and the number of babies born in the province of Drenthe, rural area. And yeah, I mean the data did match the prediction. Yeah, for sure. ASCO went up, and so did B. So there was a very nice correlation between the two. And then, so the answer here is yes. So then we go to step 6, and the question is this outcome likely even if the model does not fit the real world? In this case, I can come up with an alternative model that yields the same prediction. And the alternative model is this. The ordinary story about conception, semen, etc., etc. Well, as you can see nowadays on TV, stories about summer, that is sun, fun, and sex. And then 9 months later, after the summer, there is the springtime. And what happens in spring in Drenthe, you can see the storks flying over from on their way to the north from the south. So that is an alternative model. And the conclusion is that there is now, although the data do match with the prediction, they do not provide evidence for this match between real world and model. So the conclusion here is there is not sufficient evidence. But we cannot discard this model. It still might be true on the basis of this data. We just cannot tell. Okay. Now, how do mathematicians prove a theorem? Very often, they start by, suppose that P is true. So P implies Q, that is their a theory, there's a theorem. How do they prove it? They start by, suppose P is true, then they throw in some tricks, etc., etc., and then they arrive at Q is true. And then they say, we're done. And the question is, why are we done when we have established that, under the assumption that P is true, that Q is true? Well, in that case, let's go back to our truth tables. So here's the truth table for P implies Q. Why are we done now? Well, we start with P is true. So it means that we're either in first row or in the second row. But we're certainly not in rows 3 and 4. Well, if we then can show that Q is true, then we're sure that we're in the first row. In other words, we're certainly not in the second row. So red will never occur. So basically, if the red row never occurs, then you basically have only ones. So this suffices to prove the theorem that P implies Q. And that is what we're going to do, that is underlying the 6-step program, this type of reasoning. The rest, it doesn't matter. Now, this is a church, and some of you may be religious, others are not religious. Some of you may still be looking, questioning, whatever. And you think when you close the door here that we're now at a university and there is nothing religious about what we're doing. We're hard scientists. Well, you've just entered the Church of Science. And that is underlying also this 6-step program. Because our scientific religion is that if the model fits the real world, then the data must agree with the prediction. And that is a statement of form P implies Q. And it is our conviction that this statement is true. That is sacred. It's holy. Don't touch this. When you start touching this, things fall apart. So it is our conviction that this statement is true. And now consider the answer in step 5. Suppose that the answer in step 5 was no. The data do not agree with the prediction. Well, have a look at your truth table. We are in row 2 of 4. But thanks to our conviction, thanks to our religion, we're not here. Because our religion tells us that P implies Q is true. So, hence, this does not occur, hence P must be 0. And P was the model fits the real world. Hence, in step 5, if the answer to question 5 or in step 5 is no, then the only answer you can give, given your conviction, is that hence the model does not fit the real world. That's the underlying logical background of this 6-step method. Okay, suppose now that the answer to step 5 was yes, the data do agree with the prediction, then we have to raise a follow-up question. Question 6. Step 6. So yes, the data agree with the prediction. That was Q. So Q is 1. So we are now in row 1 or in row 3. The follow-up question is then, was the prediction likely to agree with the data even if the model does not fit the real world? Well, if the answer is well, actually, the question is it possible that the model, your model, does not fit the real world, and still the prediction matches the data? Is that the case? So actually, the question here is, could we have a purple case? Well, if we have a purple case, well, if the answer is no, we don't have a purple case, then we have a green case. And in the green case, we can conclude the model fits the real world. So if the answer to question number 6 or step 6 is no, it is unlikely, then we can discard the purple case, leaving the green case, which says P is 1. However, if we cannot discard the purple case, so if the answer to question 6 in step 6 is yes, well, then we don't know. It can be either green or purple. So that is the logical background in terms of truth tables behind this 6-step method. On the Blackboard side for this course, you will find a 16-page document that goes in more detail and more with more examples through this method. There it is, hypothetical deductive method. You will also find, and well, I'm not going into details here, you will also find a set of examples for marginal or pseudoscience. And typically, in marginal or pseudoscience, the answer is yes. So for example, my model is that there are extraterrestrials that visit this world, and they all wear orange trousers and pink shirts. and they only come by nighttime. And they construct large structures, and they have been visiting the Earth for many, many times. And actually, they build pyramids. And they like pyramids in the sand. And if you go to Egypt, that's the data. In Egypt, you have these pyramids surrounded by a lot of sand. So that is a model, and data and prediction do match. And that is a typical example where you have constructed your model on the basis of the data. So you've taken the data first, the things that you would like to predict, and then come up with the model. And in that case, refuting that model, my model of extraterrestrials with orange trousers and pink blouses, you can come up easily with an alternative model. Your alternative model is extraterrestrials with green trousers and white shirts, right? And with exactly the same predictions. I mean, and who said? So, and that is typically what happens in marginal or pseudoscience. Also, you have these stories about people predicting things, and very often with some probability theory, you may come up with the answer that, well, there is a good, fair, at least substantially positive chance that this could be just coincidence. There's also some examples about getting the data right, because what is assumed, underlying, is that the step from model to prediction is done correctly. So basically, avoid stupid mistakes. But this error is causing a lot of discussions. How do you get your data from the real world? And these are the discussions about, well, your sample was not well done. It was not a representative sample. These discussions fall into this red arrow. Okay, in a minute we're going to practice. I have some examples here, and you're going to work out your 6-step program. Two things in this class, outside the class I don't care. In this class, two things are not allowed. God and zero chances. And God is to be interpreted very, very broadly. And so, for example, I do not accept an answer like God says it's green. Every time, every year, there are people when they are confronted with a statement, they say, well, yeah, but I'm not convinced. Couldn't it be true that somewhere else on the world, coincidentally? No, bullshit. Isn't it possible that tomorrow, when we wake up, gravity will not work, and we'll all fly up to the moon? Sure, it's possible. So in this case, my counter-argument is that they wear green trousers and not orange trousers. So my argument to whatever you say is that my God tells that your God is wrong, is an asshole. And so there is nothing to discuss about. There's nothing to argue about. And here, yeah, my answer is anything is possible. If you want to use this argument, fine, but then you must at least convince me that there is a significant positive probability, unspecified. And it's a matter of taste. Well, the standard prediction is that This week you will meet somebody interesting with blonde hair. Well, I can refute about. I can use a probability theory there. Almost everybody is blonde. I mean, if we stretch the definition of blonde, even you are blonde. So that's not a statement at all. So then you can apply probability theory. And that's the point. I'm not against God. I'm not against zero chances. But here in this class, if we want to argue on the basis of scientific reasonings, God and zero chances kill all scientific reasoning. And that's why they're not allowed